What time is it? Seems like a simple question, but in a distributed system, it's one of the hardest problems in all of computer science. Imagine 3 servers spread across different data centers. Each one has its own physical clock. And here's the thing, those clocks drift. Even with NTP synchronization, they can be milliseconds or even seconds apart. Now watch what happens. Server A sends a message at its local time 10 o'clock and 1 second. Server B receives that message at its local time 10 o'clock and 0 seconds. According to B's clock, the message arrived before it was even sent. That's clearly impossible, but the timestamps say otherwise. This kind of clock skew isn't rare. It happens all the time in real systems, and it creates a fundamental question. If we can't trust physical clocks, how do we figure out what happened before what? How do we establish the order of events across machines that can never truly agree on the time? You might wonder, does event ordering really matter that much? Let's look at a concrete example. Say you have a bank account replicated across 2 database nodes. 2 operations arrive at roughly the same time. Operation 1, deposit $100. Operation 2, check the balance. If replica A processes the deposit first, then the balance check, it returns $100. But if replica B processes the balance check first, then the deposit, it returns $0. Same operations, different order, completely different results. Now imagine this happening with stock trades, or medical records, or shopping carts. The order of events isn't just a technical detail, it determines correctness. What we need is a way to answer one critical question. Did event A cause event B, or did they happen completely independently? If the deposit happened before the balance check, every replica should agree on that. But if they were truly independent, concurrent operations, we need to know that too. This is the problem of causal ordering. In 1978, Leslie Lamport published a paper that changed how we think about time in distributed systems. His insight was radical. Forget physical time entirely. You don't need to know what time it is. You just need to know what happened before what. His solution was the logical clock. It's beautifully simple. Every node in the system keeps a single counter, starting at 0. Every time something happens on that node, an event occurs, the counter increments by 1. So if node A processes 3 events, its counter goes from 0 to 1, then to 2, then to 3. Each event gets a logical timestamp, not a time of day, just a number that increases. This alone gives us something useful. Within a single node, if event X has timestamp 2 and event Y has timestamp 3, we know X happened before Y. But what about events on different nodes? How does node A's counter relate to node B's counter? That's where the real cleverness comes in. Lamport clocks become powerful when nodes communicate. There are just 2 rules for message passing. Rule 1. When a node sends a message, it increments its counter and attaches the counter value to the message. So if node A's counter is at 2, it becomes 3, and the message carries the value 3. Rule 2. When a node receives a message, it takes the maximum of its own counter and the received value, then adds 1. This is the key mechanism. Let's trace through an example. Node A starts at 0, does a local event going to 1, then sends a message to B carrying 1. B's counter is at 0. It takes max of 0 and 1, which is 1, adds 1, getting 2. Now B sends a message to C carrying 2. C is at 0. Max of 0 and 2 is 2, plus 1 equals 3. Notice how the counters flow forward. Information about A's events propagates through B to see the counter always moves forward, never backward. That's the happen before relationship encoded in numbers. Lamport clocks are elegant, but they have a critical blind spot. Let's see it in action. Look at this timeline. Node A does a local event and gets timestamp 1. Meanwhile, node B also does a local event and also gets timestamp 1. These 2 events happened completely independently. No message connected them. They're concurrent. But their Lamport timestamps are identical. The clock can't tell us whether one caused the other or whether they're completely unrelated. It gets worse. Even when timestamps are different, say event X has timestamp 3 and event Y has timestamp 5, all we can say is that X might have happened before Y, but it's also possible that X and Y are concurrent and just happen to have different counter values. Formally, if the timestamp of A is less than the timestamp of B, that does not mean A caused B. The implication only works one way. If A happened before B, then A's timestamp is less. But the reverse isn't true. We need a clock that can detect concurrency, and that's exactly what vector clocks do. The fix is surprisingly elegant. Instead of each node keeping a single counter, every node maintains a vector. One counter for every node in the system. In a 3-node system with nodes A, B, and C, each node keeps an array of 3 numbers. Node A's vector tracks A's own event count, what A knows about B's count, and what A knows about C's count. Initially, every position is 0. Here's the crucial rule. Each node only increments its own position in the vector. Node A increments the first position, node B increments the second, node C increments the third. So when node A processes its first event, its vector goes from 0, 0, 0 to 1, 0, 0. The first slot increased because A owns that slot. The other slots stay at 0 because A hasn't heard from B or C yet. This simple change, from a single number to a vector of numbers, gives us exactly the power we were missing. Each node now carries a summary of everything it knows about the entire system's history. It's like a fingerprint of causal knowledge. Let's walk through the 3 operations with a concrete example. First, internal events. Node A does a local event. It increments its own position. Vector goes from 0, 0, 0 to 1, 0, 0. Simple. Second, sending. Node A sends a message to B before sending. A increments its own slot, going to 2, 0, 0. The message carries this vector. Third, receiving. This is where the magic happens. Node B receives the message carrying 2, 0, 0. B first increments its own slot, then takes the element-wise maximum of its own vector and the received vector. B's vector was 0, 0, 0. It increments its own slot to 0, 1, 0. Then element-wise max of 0, 1, 0 and 2, 0, 0 gives 2, 1, 0. B now knows about A's 2 events plus its own 1 event. Now B sends to C. B increments to 2, 2, 0 and sends. C receives, increments its slot, and takes the max. C ends up with 2, 2, 1. Look at C's final vector, 2, 2, 1. It encodes the complete causal history. C knows about A's 2 events, B's 2 events, and its own 1 event. Every vector is a compact summary of what that node has observed. Now here's the payoff. We can compare 2 vector clocks and know exactly how 2 events relate. The rule is simple. Vector A happened before vector B if every element of A is less than or equal to the corresponding element of B, and at least one element is strictly less. Let's try it. Compare 1, 0, 0 and 2, 1, 0. Every element of the first is less than or equal to the second. 1 is less than 2, 0 is less than 1, 0 equals 0, and at least 1 is strictly less. So the first event happened before the second. They're causally related. Now compare 1, 0, 0 and 0, 0, 1. The first element, 1 is greater than 0. The third element, 0 is less than 1. Neither vector is less than or equal to the other in every position. These events are concurrent. They happened independently with no causal connection. This is a partial order, and that's exactly right. Not every pair of events needs to be comparable. Concurrent events are genuinely independent. No information flowed between them. They couldn't possibly have influenced each other. Vector clocks capture this perfectly. This isn't just theory. Vector clocks power real systems. Amazon's Dynamo paper, published in 2007, describes how they used vector clocks for conflict detection in their distributed database. Here's how it works. Dynamo replicates data across multiple nodes. When a client writes to one replica, that replica updates its vector clock. If 2 clients write to different replicas at the same time, both replicas update independently. Their vector clocks become concurrent. When Dynamo detects concurrent vector clocks during a read, it knows there's a conflict. It can't automatically pick a winner because neither write caused the other. Instead, it returns both versions to the client, which can then merge them. This is exactly how shopping carts work. You add an item from your phone while adding a different item from your laptop. These are concurrent operations. Neither should overwrite the other. Vector clocks identify the concurrency, and the application merges both additions into a single cart. Without vector clocks, one of those additions would be silently lost. With them, the system knows to keep both. Vector clocks are powerful, but they're not free. The most obvious cost is space. Every vector has one entry per node in the system. In a cluster with 10 nodes, each event carries a vector of 10 integers. That's fine. But in a system with 10,000 nodes, every single message carries a vector of 10,000 integers. That's significant overhead. Researchers have proposed solutions. Interval tree clocks, dotted version vectors, and other approaches can compress or bound the vector size. But the fundamental trade-off remains. More precision about causality requires more metadata. Let's recap what we've learned. Physical clocks fail because they drift and can never perfectly synchronize. Lamport clocks give us a logical ordering but can't detect concurrency. Vector clocks solve this by having each node track what it knows about every other node. The comparison rule is elegant. If every element is less than or equal, it's causal. If elements go in different directions, it's concurrent. Physical clocks tell time. Lamport clocks order events. Vector clocks reveal causality. And in distributed systems, understanding causality is everything.